Hello everybody, this is Reginald Ford. Most people know me as Rex. I was playing around with some complex analysis and realized that it's not that hard to prove the quadratic formula. So, without further ado, we're going to begin with the general quadratic equation. ax squared plus bx plus c equals 0. Okay? Now, we're going to assume that a, b, and c are real numbers, so they're in the power set of the reals. They're just regular old numbers. But we're not going to assume that x is real. So x is just a general complex number, r times e to the I theta. Alright? Now, we plug that in, and we end up squaring the r. E to the I theta squared is e to the I 2 theta. And then we just have the rest of the equation with e to the I theta plugged in for x. Or r times e to the I theta plugged in for x. Now, this means that 3 vectors have added up to 0, okay? 3 vectors on the complex plane. So I drew that picture here. Alright? Now, some vector plus another vector equal to 0. Now that we can turn this into 2 different pictures, 2 different one-dimensional pictures, by taking their projections onto the imaginary and real axis. So if I took the projection of this onto the imaginary axis, plus the projection of this onto the imaginary axis, plus the last vector's projection, then they should actually add up to 0. And the projections onto the real axis should all add up to 0. Okay? The reason I drew it this way is because this vector right here is c. That is a real number and has no imaginary part. Alright? So let's take the projection onto the imaginary axis. That would be ar squared sine 2 theta plus br sine theta equals 0. Alright, now c never contributed to this part because it doesn't have an imaginary part. Now, we have a sine of 2 theta, so that triggered in my mind to use the double angle formula. So I did that. Sine of 2 theta is 2 sine cosine. I also pulled out an r because I have an r in both of these terms. So I pulled out an r and I pulled out sine. Now, from this point I basically thought about it. If r was 0, this would be the general truth that r is 0 for all the solutions to our quadratic equation, you know? And that would mean that we have a double root at 0. Now, if sine theta was 0, that would just tell us that we have a real number. And to figure out any more, we would have to use use the rest of this equation. So it's this factor that actually gives us some information. If 2ar cosine theta plus b equals 0, then we can solve for r cosine theta, and we end up with this. And r cosine theta happens to be the projection onto the real axis of our solution. So we know the real part of our solution is negative b over 2a, which makes sense. That's half of the quadratic formula. Alright, so we're halfway done. Now, we're going to take the projection onto the real axis. Okay? This would be the same equation as before, but with cosines. And we have c contributing to the projection onto the real axis. Just like the picture suggests, c is involved in the projection onto the real axis. So, we know where we're headed because we want to show that r sine theta is plus or minus the square root of b squared minus 4ac over 2a. The plus or minus is kind of automatic for square roots. So what we do is we pull out r, because we have r in these 2 terms, but it is not in the c term, so we just pulled it out of the other 2 terms. And we're going to do a trick here. The trick is that we know cosine theta is negative b over 2ar. How do we know that? Because that was our non-trivial result from before. The real part was negative b over 2a. We just divided both sides by r. So cosine theta is negative b over 2ar. So I know that. I also have the double angle formula for cosine. It's cosine squared minus sine squared. So I have r times AR, here's cosine 2 theta. Oh, by the way, when I use the double angle formula, I have cosine squared theta here. When I know cosine theta is this, so I squared this, and I ended up with b squared over 4a squared r squared. That's why that's gone there. But I left the sine squared from the double angle formula as sine squared. Why? Because I ended up with something I want on the left side of the equation. I want sine here. That's what I want to show. So hopefully later on I'll have to square root something and end up with something good. So I distributed this now so that I have no more parentheses. And basically you get this. And from here it's just a lot of algebra. Not even that much really. But I solved the equation for r squared sine squared theta. And the last thing I had to do was divide by negative a. So that's why there's a negative a there. And you end up with this. Now, with these two guys on the top of the fraction, I could easily make them have a common denominator, so I did. And the top ended up being 2b squared minus b squared. And hey, that's b squared. So I square rooted both sides. And I ended up with that r sine theta is the square root of all this. And then I was thinking, how do I get it to look like the quadratic formula, the last part of the quadratic formula? Well, I multiply the top and bottom by 4a. So now I have 4ac minus b squared over 4a squared. Now this is the top part multiplied by 1 over 4a squared. And if I wanted to pull that out, I have to square root it. And square root of 4a squared is 2a. So that's how you ended up with 2a on the bottom. And that's the last part of the quadratic formula. So x is negative b plus or minus the square root of b squared minus 4ac over 2a. Plus or minus is automatic for this situation because square roots have two solutions. One is the conjugate of the other, and so that's why there's a plus or minus there. And that is how you prove a quadratic formula. So, I hope that was fun for you guys. It was certainly fun for me. And until next time, don't divide by 0.